Good morning and good afternoon, Eaton Nation. I'm Josh Kingsley, your host for today's final Ask the Expert event of the year. In this month's session, we're going to be taking your questions about inductive proximity sensors. So let's start with meeting our expert for today. Please say hello to your Global Product Manager for Sensors, Mr. Matt Sims.
Hey, good morning, Eaton Nation. Great to be here. I'm out here in sunny Seattle, Washington, and looking forward to the session. And sunny is a little bit of a euphemism for overcast, the first two non-rainy days in the last 4 months out here in Seattle. So we're going to enjoy it. Looking forward to this session. Thanks, Josh.
Yeah, glad you guys finally got a little bit of sun. It's nice. You should try it more often. All right, great to have you, Matt. Let's start by getting some housekeeping out of the way. To you, our audience, you can ask questions like usual via the comment sections below on either LinkedIn or Facebook. And in this month, we've got a free download, and it's a training manual, and it's called The Basics of Inductive and Capacitive Presence Sensing. So make sure to stick around through the end of this session, and we'll show you exactly how to get it. And this Ask the Expert session is brought to you by Eaton's E57G Inductive Proximity Sensor. Please visit eaton.com/E57 to explore the portfolio. And once again, that is eaton.com/E57. Want to get into the first question, Matt? How's that sound?
Perfect. Let's go.
All right. So our first one is going to come from Jerry on LinkedIn, and I think this is going to be a great way to start. His question is, what's an inductive proximity sensor?
Yeah, it's a nice softball question. But if you're unfamiliar with these kinds of electronic sensors, it's a good place to start. So the two instructive words are inductive and proximity. We'll use proximity first. So proximity sensing means an electronic sensor that does not require the target to actually contact the sensor physically in order to be detected. That's the proximity part. You know, if you compare it to like a limit switch, where the target has to actually physically contact the switch operating lever to make the switch change state. In a proximity sensor, it's electronic, and the target only has to come in proximity of the sensor. The inductive part means it's a sensor designed to detect metallic objects. So inductive proximity, metallic objects where the target only has to come within a certain distance of the sensor in order to be detected.
Got it. All right. Thank you for the level set on that one. I appreciate you getting the audience all on the same page. And again, thanks for that question, Jerry, to start us out. We're going to stay on LinkedIn for this next one. And this one's coming from Daryl. His question is, how does an inductive proximity sensor actually work? Which I think is a good next question.
Yeah, another good question. So probably easiest to look at, I got some parts around here. We've got a block diagram we can share into the environment that shows kind of the building blocks of an inductive sensor. That's probably a good way to start. If we can find that image, yeah, that's perfect. And I can show you kind of here of what we're talking about, what you see in the picture there. So you see a couple of component parts of the sensor in the front end, and what we kind of see here is what we call the transducer. Basically, it's the sensing part of the device. It's a coil of wire and a ferrite core wrapped around a ferrite core that creates a field. Behind that sits an oscillator circuit. That oscillator circuit that you see in the block diagram creates an electromagnetic field, basically at radio frequency kind of levels. And that oscillator circuit feeds up to that coil, and that coil and core shape the field as it emits from the front of the sensor. When that target then comes in to the sensing environment, that electromagnetic field from the sensor induces eddy currents, what are called eddy currents, in the surface of the target material. So those currents start to flow, and that dampens our oscillator-induced signal, and that damping is detected in our detector circuit. So that's that third block in the block diagram there. So we sense that the electromagnetic field from the sensor is being dampened by the presence of the target, and then the detector circuit recognizes that as a valid detection, and it switches the output for the sensor. So a sensor turns on or off depending on the type of sensor it is, based on that chain of events.
Got it. Perfect. Perfect. Thank you for bringing that graphic up and explaining that. All right. Next question we have is going to come from Facebook. This time it's from Sarah, and it looks like she's throwing out a scenario. So the scenario, if I can sum this up here, the scenario is changing from a limit switch to a non-contact device in the application. And what's the potential for interference from other metal in the area where the sensor's going?
Okay, no, that's a great question. I'll show you that kind of in the framework of a sensor like this. This is, kind of a real sensor in a real application. We'll talk about this in a second. So the limit switch application, very typical, common to be transitioning, an application on a machine from a contact device like a limit switch to a non-contact device like a proximity sensor. And the limit switch, like I said, requires the target to actually contact the switch lever. Once you've got that sorted out, you really don't have to worry about what's going on out in the sensing environment. In this case, you've got an electronic device like this sensor, and you can see it here mounted on this bracket. So this is designed to sense metallic objects that we talked about, but you've got obviously metal nuts that mount this sensor onto a bracket like this bracket here. You're not so much worried about those things. The sensor is designed to avoid any objects like that. The tube, the sensor is built in, the nuts, the mounting bracket, that sort of thing. Where you need to be concerned is the metal that's in the target detection zone. That's the greater concern.
Okay, so get a little bit more into detail. If there is going to be a possibility for interference, how do you mitigate that? What's the process of going through that?
Sure. And we can show that picture that we showed at the very beginning, the family of sensor picture. We could maybe pull that back up. That's a good example. Yeah, that's perfect. So there are different sensors designed to account for the presence of other metal in the target area. Obviously, you want to detect the target. You don't want to detect some other metal that's in that area. And we've got a couple different types of sensors. You can see them in the picture there. Let me find one. So here's an example of that sensor that you see on the left, where the cap of the sensor is flush to the tube. That's what's known as a shielded sensor. Those sensors are suited to be mounted directly into a metal surface, flush to the metal surface, and they have a much more narrow beam profile or field profile, so that it's more, that type of sensor is more resistant to other metal in the target area. There are other sensors that are known as unshielded sensors. You see that in the picture, the sensor in the middle and the sensor on the right, where the cap of the sensor, where that coil and core are extended from the front of the sensor. Those sensors have longer ranges and are less resistant to detection of metal in the area. You cannot embed those in the surface, directly into a metallic surface in the machine or wherever the application environment puts you.
Got it. So the main downside with a shielded sensor is having the reduced sensing ranges compared to unshielded. Is that correct synopsis?
It's very typical. And we've got another graphic, if you guys can find that, a graphic of those two types of sensors that I just described actually embedded in a typical mounting surface.
Yep,
that's it. Yeah, that's it. So if you look, there's that sensor on the left is the shielded sensor, meaning it can be embedded directly in the surface. You can see that's flush to the surface, that's embedded in metal. It's not going to detect the metal. It's going to detect the target as it approaches in the detection zone. You can see that the sensor on the right is the unshielded device you just mentioned. It's got longer range. Typically, the sensor on the left, if it has a range of 10 millimeters, say, the sensor on the right is going to have twice the range. So it might see 20 millimeters. But if you need that kind of range, you need to account for metal in the area of the target detection, as you see in that graphic, providing space on either side of the sensor, providing space beyond where the target's detected. So, with these kinds of guidelines, you can apply even that unshielded sensor when you've got the potential for interference from metal in the target area, like Sarah, I think, asked in the original question.
Got it. Yeah. So, I mean, it kind of sounds like an old school CB radio where you can turn the squelch up and get a clear signal, but you cut down on the distance that you can go. So it's the type of stuff that you have to trade off. And I mean, I think this is the first really good example we have on this one. Like every other series, the thing always comes up. Just make sure that you have as many application details up front as possible. Know what kind of parameters you're working with, what you're trying to accomplish, and what kind of external factors will be coming into play. So thanks for walking through that one.
Breaker 19, Josh.
Breaker 19. Yeah. We got a convoy going. All right. The other thing we have besides a convoy is a ton of questions coming in. So thanks to Eaton Nation for that. But the producers are letting me know that I do need to tell you that this episode of Ask the Experts is brought to you by the E57G inductive proximity sensor. Make sure to visit eaton.com/E57. And once again, that is eaton.com/E57 to learn more about the product. So let's jump over on this one. We're going to go to LinkedIn, and this is Chetan. So I'm hoping I'm pronouncing the name correctly. And this is a pretty high level question. What's the basic principle of a proximity sensor?
Yeah, again, the basic principle is that you use the electronics in the sensor circuit. So this, example of this is a typical sensor circuit board to create an electromagnetic field. So that's one step, right? The second step is you need to somehow direct that field into an area in the vicinity of the sensor where you want target detection to occur. And that's the purpose of this coil and core. So you create an electromagnetic field, the core and the coil shape that. And if you take, in this case, here's a tube, you take that now, that core and coil shaping creates the field directly in front of the sensor, so that creates the target detection zone. So again, the principle is the creation of an electromagnetic field, and then that electromagnetic field is disturbed by the presence of that target in the way we described earlier. And we were able to detect that disturbance. So,
Matt, we're getting a little bit of vocal interference. Can you double check your connection? Make sure we can hear all this good info you're giving us.
Okay. Can you hear me?
That sounds good right there. So whatever you did, let's keep that going. All right. So next one that we're going to run with is also from LinkedIn, and this is Lufano. And the question is, where would you use such a device? So I think what we're really trying to find out are what are some good common applications for inductive Prox sensors?
Sure. So these sensors typically, again, they're used for sensing metallic objects. One of the primary areas where they're applied is sensing the moving parts of a piece of equipment, a machine where there are moving pieces. There are gates, there are shafts rotating, there are arms moving back and forth, there are slides, there are hydraulic cylinders moving things back and forth to create a movement of a product or a movement of an object that's being manufactured, conveyed on this piece of equipment. So those internal moving parts of a machine, typically those components are metal or metallic. And so an inductive proximity sensor can be used to sense that a cycle of some part of the machine has been completed. For example, if that cylinder has pushed the ram out to the extended position, detecting that, or that has retracted back to the base position, detecting that. When you're talking about actually looking at materials that are produced, for example, on a piece of equipment like bolts, in a machine like that, or stamped parts in a stamping machine or a press. Again, many of those are metallic objects, and a proximity sensor can be used to detect those, for example, when they're being manufactured, counting them at the end of the process, looking at a particular feature, something that's being welded onto one of those components. So you can look at the internals of a piece of equipment or a machine, and you can also look at the components that are being produced by that machine or moved by that machine if they're metallic in nature.
Got it. So this is a quick follow-up for me. You're talking a lot about metallic objects. Is there a difference between ferrous, non-ferrous. Really what I'm saying is, are you detecting steel, aluminum, both? What are some of the things to consider with that?
Sure. So in that range of metallic objects, inductive proximity sensors are rated by international standards organizations, and those standards organizations set criteria for inductive sensor performance. They have that, and that means there are standards for targets. So that sensor that I talked about earlier that's rated to 10 millimeters, that 10 millimeter rating is to a certain type and size of target. Typically, it's a mild steel target that's a square, 1 millimeter thick, and it's square to be the size or very close to the size of the sensor itself. If you are using a target or you have a target in your application that's other than mild steel, almost all inductive sensors require some kind of adjustment factor. For example, you talked about aluminum. Typically, aluminum is detected at roughly 50% of the range of mild steel. So if you have aluminum targets, you need to adjust that 10 millimeter sensor to be 5 millimeters away from the target. So, and then once you get outside the realm of metallic objects, you need to go to some other kind of sensing technology. You mentioned capacitive sensing. That's typically used for sensing plastics and non-metallic objects. And there are photoelectric or optical sensors that are used for those types of targets as well.
Got it. Perfect. All right. So next one, this one comes from Nelson on LinkedIn. And the question is, does partial discharge have any impact on how this works?
That's you win that one, Nelson. That's a term that's not commonly used in inductive proximity sensing, so I'm not 100% sure what that question means, Josh.
Okay, perfect. So Nelson, please feel free to add some clarifying comments, and we can try and circle back to that one, or have one of our tech guys see if we can answer that through the chat. But yeah, you get the prize for stumping the expert today.
That's great. That's a new one.
All right, so here's another one from LinkedIn coming from Dan. Is this an analog or digital type of setup?
So inductive proximity sensors are available in both modes. So typical sensors are digital in nature. Most commonly, they're 3-wire devices with transistor output, either a sourcing transistor, PNP type, or a sinking transistor, NPN type. So it's digital sensor on off. But inductive proximity sensors are also manufactured in analog versions. So where the distance to the target, the output is proportional to the distance to the target. Those sensors typically have outputs either 0 to 20 milliamp, 4 to 20 milliamp current outputs, or 0 to 10 volt voltage outputs. Again, the output being proportional to the distance of the target to the sensor.
Got it. Okay. I'm going to do another one that we have from LinkedIn. This one's coming from Luann, and this is going to kind of follow what you were just talking about. What are the wiring options when it comes to inductive proximity sensors?
That's a great question. That's probably the most common question we get when it comes to inductive sensor applications. And we've got a couple of graphics, if we can find those, that look at the 3 or 4 wiring types. Yeah, that's perfect. So this is a good starting point. So the most common wiring type when you enter the world of inductive proximity sensing is a 2-wire wiring system. And most commonly you're coming from something like a limit switch, where there are just 2 wires, and your power to your sensor and your power to your load are the same. So imagine that sensor is a limit switch, and you got your load. When the switch is off, the circuit is open, there is no current flowing. You put an inductive sensor into that circuit, a 2-wire inductive sensor, and all of a sudden the sensor needs some power to stay alive and operate in order to detect the target and turn that load on or off. So you have what we call a residual current, and that just means that the sensor, that circuit in an inductive sensor mode will be, or a application will be always drawing a small amount of current, where in the case of the limit switch in that 2-wire circuit, the circuit's open and it's not drawing any current when the circuit's off. So then there's another graphic you guys can pull up that shows a 3-wire circuit. So that was 2-wire, limit switch kind of wiring. This is more common 3-wire circuit, and the third wire is the output wire. So the power to the load and the power to the sensor are separate. In this case, this is a PNP output. So when the sensor switches on or off, that current flows from the sensor through the load. And then if you pull up the next graphic, we've got an NPN graphic that shows, again, a syncing circuit. It's not as common in North America, more common in other parts of the world, but certainly present, here in North America. Again, typical 3-wire circuit. And then you might also hear sensors referred to as 4-wire devices. Sometimes you hear 5-wire, you hear 6-wire. Mostly what that means is a sensor that's got power wiring plus multiple output circuits. So in this case, an NPN circuit and a PNP circuit in the same sensor, that would be a 4-wire device. And if you had, for example, 2 output circuits on 2 complete, solid state transistor output circuits on a sensor, you might see a 6-wire sensor. So, but the most common are 3-wire devices and 2-wire devices when you talk about replacing something like a limit switch.
Got it. I can definitely tell that question comes up a lot. Thanks for that really thorough explanation. Thanks for the question, Luann. And yeah, love the graphics. So I'm going to throw 2 questions at you at once here that I think are going to kind of tie together. So this is a follow-up from Chetan on LinkedIn, and it's also from Muhammad Hassanin on LinkedIn as well. And so the first is a follow-up, which is, what is the sensing distance of an inductive sensor? And then the next one is, how long is the detection time between the object presence and the signal output? And I feel like those are going to kind of tie together based on some of the application details we were discussing.
Sure. So detection distance, just as a basic concept in the world of inductive sensing, and I showed you a tubular kind of type of sensor in some of the earlier examples. There are other, form factors of sensors. This is a cube style 40 millimeter device. You can see here's another one that's a limit switch size device. Each one of those has different range performance characteristics, but most typically you'll see sensors that have ranges out to a maximum of about 100 millimeters or 4 inches roughly in the world of industrial inductive proximity sensors. And to get a 4-inch or 100 millimeter range, you need to have a fairly large sensor device, because typically the sensor can see about as far as its diameter, physical diameter. So in this case, this cube is 40 millimeters square. The maximum sensing range of that device is roughly 40 millimeters. This tubular sensor is 30 millimeters in diameter. As far as it can see is roughly 30 millimeters. So think about it in those terms. And if you need a 100 millimeter sensing range, the sensor's got to be 100 millimeters in diameter. And it's just physics at work. And then you talked about, and it's kind of the second part of that question was the detection time between when the target is detected and the output switch is on.
Can you double check the audio real quick, Matt? Sorry.
Can you hear me okay?
Yeah, we're good now.
Okay, so that time between when the sensor, the target is actually detected by the detection circuit and the output switches is a very short time, typically called a dwell time. And the characteristic of that is unique to the particular circuit for the particular sensor you have. So you can typically find that in the data sheet for a sensor. You'll find it referenced as something like dwell time. Some people call it different things, but typically it's very short in milliseconds or microseconds. But it's something that you may need to know for your particular application.
Got it. And that's going to come into the speed that the material is moving, correct? That's where that's really going to make a difference.
Yeah, that's one aspect of it. Another, really the biggest aspect of performance when it comes to the speed of presentation of material is the response time of the sensor. And you'll see inductive sensors rated in response time in hertz. So you'll see a typical 18 millimeter diameter inductive sensor might have a response time of 1,000 hertz, so 1,000 cycles per second. So that's how many targets can present themselves and be detected by the sensor. So if you want to know about detection rate. You want to look for that response time spec in a data sheet. And typically as the sensors get bigger, the response time gets slower. So the smallest sensor is going to have the fastest response and to be able to detect the most targets in a given period of time. And the larger sensors are going to have a slower response because of the amount of signal processing required to handle the changes in the field that you see for a bigger sensor. Got
it. Great. Next question. Sunny from LinkedIn is wanting to know, actually, sorry, this one's coming from Facebook. Does the size of the object have any kind of factor that goes into this? You've talked a lot about sizes of objects, so let's expand on that. This is a good time to ask that question.
Yeah, well, we talked about that when we talked about the standards. You were asking about that earlier question about different target materials. So as sensors are rated to that standard mild steel target, they're rated to a target of a certain size. And the takeaway you want to have is you want the size of the sensor to roughly match the size of the target. And it's not so much a big deal if the target's bigger than the sensor. You know, if you got a plate of steel that's 10 inches square and you're detecting it with a 30 millimeter sensor, that's going to be fine. But if that target is very small, you want the sensor to get smaller with it. So if that target is only 12 millimeters square, you don't want to use that larger sensor to see it. You want to use a 12 millimeter diameter sensor because of the effects. You can get some strange and unpredictable range effects when you use a bigger sensor on a small target. And you can also have effects on that response time issue we just talked about in that last question. Your response time can change if the target gets small relative to your sensor. So just think, if I've got a small target, I want a small sensor.
Got it. Application details are the key. Sounds like a good reiteration of that. All right, so we have two questions, one from Facebook, one from LinkedIn, and one is from Discharge, and the other one can't locate the name. Success stories with inductive proximity sensors. What would you say is a good success story for this type of application? Let's maybe think of an application that you've been part of where this has been highly effective and sure, truly got the job done.
Sure. So we were talking about the different types of applications. So detecting movements of a machine or detecting things that the machine is actually moving. So I'll talk about two different examples. So first example is the movements of the machine. Something most machine builders and people who own and operate machines care about is something called throughput or yield. How many parts can I get through a piece of equipment over a certain period of time? And inductive sensors in the internals of the machine can improve your throughput by giving you specific data, time sensitive, time real data on what the machine is doing. For example, has that arm retracted fully? If I know it at a specific point in time, then I can take the action to move the product to the next station. And if I know that immediately and can take that action in a timely manner to follow, then I can improve the throughput of the equipment. So in using an inductive sensor to know precisely when a machine movement has occurred is a way to show success in something like a throughput improvement. In the example of something that that a machine is either making or conveying, one really interesting use for an inductive sensor is as an inspection device. For example, you're taking that square of steel that you're manufacturing and you're going to drill a hole in it and you're going to weld a bolt to that or a nut to that hole, and you want to inspect that. You can inspect it a lot of different ways, visually with a camera, vision system, lots of different means. But you can often do that with a simple inductive sensor. And the sensor is set up to detect, for example, the bolt. And if the bolt is not present, it's not detected because it doesn't have the range to detect the metal plate itself. So you can install something like that very inexpensively and simply to do an inspection that might be much more complicated by some other means. And in so doing, you improve the quality of a particular process. So you know that those parts are coming out with that bolt welded in the proper position, just with the simple use of an inductive sensor.
So it sounds like you're kind of using some of the constraints we talked about earlier when you're using distance and where you're using size, and you can use that as part of a quality process. That's that's interesting stuff there. Mm-hmm. Yeah, got it. Yeah, again, application details. We're at about halftime for this event, and again, thanks everybody for all the great questions. Do want to do another quick shout out to the E57G inductive proximity sensor. Make sure to visit eaton.com/E57 to learn more about the product. All right. Next question that I want to get into. This is actually two that have come in separate comments from Muslim on LinkedIn. And so first is suggestions for level measuring in a cement silo. And then what type of sensor would you use for sensing liquid particles?
Yeah, so that level sensing application, just as a general point, is most commonly accomplished with a different type of proximity sensor, a capacitive proximity sensor. We mentioned it earlier. It's going to be in this training manual that you're going to be able to download here at the end of the session. So that capacitive sensing technology allows you to detect non-metallic objects like liquid in a tank. So that in that silo, or grain or plastic pellets or things like that that may be in a container of that type. And typically there's two ways to do that. Kind of the two-part question kind of got to those two ways. One way is to actually embed the sensor in the silo itself, in the side of the silo or the side of the tank. And as the level rises in the tank and covers the sensor, that level's detected. So typically you'll have in a large tank 2 or 3 sensors, one at a low level, one at a mid level, and one at a nearly full level. And there's other ways to accomplish that. Like if you're talking about a silo, there's there are sensors like radar and other types that can look down into a tank like that and give you much more precise sensing, distance and fill level information. But they're much more complicated and much more expensive. You put a couple of sensors in that silo, a 25% level, a 50% level, and a 75% level, and you've got enough data for your control system to operate. Now, part two of the question, the other way you can do that, so say take a liquid level tank where you've got some material in a tank, and most commonly you'll have something like a sight glass on the side of the tank where you can physically see the level of the tank in the tube. That's some sort of poly material Tygon or something like that. You can install capacitive sensors adjacent to that sight glass and detect the level of the fluid, whatever the liquid is, in the tube itself as the level rises and falls. So same sort of thing. Instead of embedding the capacitive proximity sensor in the tank or the silo itself, you're just attaching them to a sight glass that's outside the tank environment. If you don't want to penetrate the tank or the silo with, by putting holes in it to install sensors. So either way, you can sense that non-metallic material, grain, plastic, those kinds of things, or liquids by direct measurement or by monitoring something like a sight glass.
Got it. Perfect. All right. Got a couple of questions that are cut from the same cloth. And the first one is operating temperature range. And this is coming from Zafar on LinkedIn. And then we also have Jorge on LinkedIn saying, what happens to an inductive proximity sensor over temperature? So let's talk about temperature a little bit.
Okay. We've actually got a temperature graphic in our training manual that we can probably pull up while I'm talking about it, if we can find that one. It's a horizontal axis has got temperature on it, and sensing distance is on the vertical axis. Yeah, perfect. Okay. So just as a general topic, so if you look at a typical inductive sensor for an industrial application, it's got a pretty broad temperature range, typically minus 25 degrees Celsius to plus 55 degrees Celsius, or even minus 40 C to plus 70 C or plus 80 C. So pretty broad temperature range. And the electronics in a circuit like an inductive sensor, these electronics can be sensitive to temperature. So those same international standards organizations that define the target characteristics to give you a rated sensing range, that 10 millimeter range to that mild steel target, They also define how much your sensor range can change over that temperature band, and that's what you see in that graphic. So the standard, international standard, is a sensor can vary up to 10% across that full temperature range. So from that 10 millimeter sensor can range from 9.1 millimeters to 10 to 11 millimeters over that full temperature range. What you see in this graphic is it's more common. The average sensor varies about 5%. You can see that over the statistical data we develop over time. Shows a variance of about 5%. And you can see it, that's 5% is what you see at the more extreme ends of the temperature spectrum. So your range is going to go out. That 10 millimeter sensor is going to see 10.5 millimeters at the extreme cold and extreme hot. And just as an aside, so how we do that is when we develop a sensor, we do extensive, what we call temperature compensation across this full range. Because if you just take a standard electronic circuit and you don't compensate for temperature, you might have a variance of 30, 40, 50% in range, which is not practical. Obviously, if your 10 millimeter sensor only sees 5 millimeters when it's cold and sees 18 millimeters when it's hot, that's not great, right? So that temperature compensation that we do, sometimes it can take months in the development process to accurately compensate a complicated or complex electronic circuit for temperature to get the results that you see there in that graph.
So this would be a lot of the same process you would go through with different control items where you have to derate based on temperature and altitude, things of that nature. Just environmental factors play a part.
Well, and that standards organization requirement that we contain that variance within 10% is what allows people to not have to deal with those adjustments, right? If you know that it's going to stay in that 10% band, then you normally don't have to worry about it.
Got it. Perfect. All right. So I'm going to jump into another application question here. This one is from William on LinkedIn. So I'm going to try and summarize this. So the AC field from the coil is resonant and the inductance of the coil without other metal present. When the other metal is detected, it disrupts the magnetic field and the circuit detects that it changed in the magnetic field. And I think that's a question. So
that's correct. Yeah.
Okay.
So William is exactly correct. So we create that field. That field exists oscillating in front of the sensor, and we are looking for a disturbance in that field. And a metallic target creates that disturbance. It dampens the field level, and the detector circuit sees that damping, and it takes a certain threshold to do it because we want to make sure we're detecting valid targets. And we also process that detection over a certain period of time. Typically, we look for a number of sequential positive detections. So we don't just a single detection, we don't consider a valid target. We'll look for a series of detections. So we look for a level of damping, and we look for a time-based to reach a conclusion, to reach a valid target conclusion and switch the output. So that's part of that response time calculation. That's part of that dwell time that we talked about in that earlier question, is just that we want to make sure that we are turning the output on when we have a valid target.
All right, perfect. This next one is coming from Mario on LinkedIn, and the question is, explain the leading edge versus trailing edge when it comes to sensing and any factors you would need to consider.
Okay, yeah, so that's most typically, so like take that metallic target, that 10-inch square target that's passing left to right in front of your sensor. So you hear those terms leading edge and trailing edge related to your control system. So if you want to know when that target enters the zone, and you want to know when that target leaves the zone in front of the sensor. And so the entering the zone is the leading edge detection, and the leaving the zone is the trailing edge detection. And there is a time associated with both of those that the sensor takes in order to, like I said, reach that determination that you have a valid target. So that sensor first enters the zone. The target first enters the detection zone. That's the leading edge of the target, like the physical leading edge of the target is in front of the sensor. The sensor hasn't yet decided it's a valid target. So if you take that, square wave and you overlay that with the sensor output, there is a lag time for the sensor to create that same leading edge, mimic the leading edge of the physical target. And then there's also a lag time associated with the sensor releasing the target. And that's a factor called hysteresis that we can talk about if someone else has a question on that. But again, you imagine that leading edge, trailing edge of the physical target is going to be overlaid with a leading edge, trailing edge profile of the sensor output and just shifted in time slightly to the right because of the need for us in the sensor to determine the target validity.
Got it. Okay, so next question. We have Ahmed from LinkedIn, and then this is also another question from Chetan on LinkedIn. So the question is, for an inductive sensor, how can the metal type affect the sensing distance? And then it also, Chetan's asking about the sensing distance. So I think you covered the sensing distance based on the size of the actual sensor itself. And then I believe you also mentioned something about derating the sensing distance based on the metal type. But if you can kind of walk back through those again real quick.
Sure. So that, again, the default target sensor, this sensor that I picked up earlier has a rated range of 15 millimeters. So that 15 millimeter range is to a mild steel target that in this case is a 30 millimeter square. So 30 millimeter diameter sensor. So if you, to address the material question, if you have a target that's not mild steel, that's something else like aluminum, like brass, like copper, you'll typically find a derating profile that says instead of 15 millimeters, apply a 50% factor to that range or a 60% factor. Stainless steel is typically very close to mild steel, but something like brass may be only a 30% factor. The other things that you need to look at, all these examples are with a flat 1 millimeter thick square of steel, right? There are lots of targets that look like that, and there are also lots of targets that don't look like that. So if you're sensing something like a steel cable is a good example, where it's like a cable at a ski resort, like a ski lift or a tram or a gondola kind of cable, where it's a multi-part, it's a multi-strand steel cable. But if you look at it from the side, it's a rough, it's a bumpy surface, it's got gaps, it's got voids, it's got, all those kinds of things. So when you have any kind of target like that, it's a square that's got holes in it. It's a, rough surface like that. It's a bumper on a car that's got, curvature to it. Or it's got convex and concave elements in the same piece. All those things can affect the sensing range. And you've talked a couple times, Josh, about the need to understand your application environment carefully. This is one kind of general takeaway we always recommend whenever we're talking to someone about inductive sensing application, is that it's always best to test the sensor that you've chosen in the application before you make final decisions on what you're doing and how you're doing it. So that, for example, that cable example, there are very interesting, when we talked about eddy currents earlier, they're very interesting eddy current profiles in something like that that's got many, many strands of steel all twisted around each other. So you can get sometimes some very extended ranges, sensing ranges. That 15 millimeter sensor might see 25 millimeters to a target like that. Or in some cases, it might only see 6 millimeters to a target like that. So as you get into more complex targets, it's always best to test the sensor you choose in that application. Just one sensor, one application, you can, in one example, one machine example, you can very quickly profile it. The sensors are going to be very consistent one to another. So if it works once, it's going to work across 1,000 sensors. But test the sensor you have, because those target characteristics can be very different, even for two targets that look completely similar to the eye.
Got it. All right, got a handful of different questions on ratings, so I'm gonna throw these out. First question is from Discharge on LinkedIn, and it's asking about safety certificates for this range of products. Then the next one is, do we have any EX certified devices? That one's from Muslim on LinkedIn. And then Tom on LinkedIn is asking if we have any shock and vibration. So EX certification, shock and vibration safety.
Sure, that's a loaded three-part question, but we'll we'll just kind of chip away at it. So so safety. So yeah, so certain sensors of this type, electronic sensors, inductive proximity sensors, carry what are known as human safety ratings. So there are, if you do there are standard processes for doing a risk analysis on a piece of equipment, where you evaluate the risk of injury, that this machine that creates by its normal.
Talking sills and performance levels, right?
Yeah, and you then cascade down through your risk analysis and decide, okay, because this process has this risk, I need a safety rated control associated with this process. And part of that safety rated control can involve a sensor that has an actual safety rating. So you can find sensors, typically not your standard industrial sensors, but kind of on the fringes of a sensor product offering from us and from other manufacturers. You can find sensors that carry those SIL ratings against the various, ISO and EN standards that apply to human safety devices. So yes, you can find sensors with those safety ratings when your risk analysis demands it. If your risk analysis doesn't say you need a safety sensor, you can apply a standard industrial sensor without those ratings. The second category you talked about was EX. That's typically explosion-proof environments where there is a risk of explosion. And you need a sensor, that's not going to cause those, whatever gases in that environment to ignite and explode. So sensors carry ratings against a couple of different, standards organizations, ATEX. They're also in North America, you'll see like class codes, class 1, div 1, class 1, div 2 ratings applied to sensors based on the environment. It's very similar to the risk analysis in that safety example. You're analyzing in this environment, what is the risk of explosion? Are you in the actual explosive environment? Are you adjacent to the explosive environment? Are you outside the explosive environment? And you have to pick a sensor with the appropriate ratings, and we have them in our portfolio, as do other manufacturers, that carry the ratings to be in whatever zone, explosion zone you're in. So just identify which that is, and then from the sensor data sheets, pull the sensor that has the appropriate rating for that example. And then your third one was, remind me?
Shock and vibration.
Oh, shock and vibration. Yeah, shock and vibration is a more standard, where those first two examples, safety is a rating to an external, standards body. That shock and vibration ratings are part of the international standards, but typically they vary more widely between manufacturers. You can meet the minimum thresholds for shock and vibration, but many times you'll see manufacturers go above and beyond because the applications out there, in many cases, demand it. We talked about that stamping equipment application earlier, where there's, where there's high shock loads. If you got an application like a conveying application where you're conveying aggregate material like gravel, rock, those conveyors vibrate, low frequency vibration. Those shock and vibration levels can be many times what the international standards agencies require. So if you have those, if you have those more extreme requirements, you can look for products that have higher levels of shock and vibration performance. A lot of times the core design of the sensor, this portion of the sensor, the electronics need to be protected against shock and vibration, and you can do many different things the way the sensor is built from here in order to give you those higher levels of performance. So identify the level of shock and vibration that you expect to see in the application environment, and then you'll be able to find a sensor that carries the appropriate ratings for shock and vibration so that the sensor will survive long-term on the equipment.
Got it. Application details.
Yeah.
Work through your data sheet and make sure you test the stuff before you go and start down a long-term manufacturing process. Perfect. All right. Next question. Here's a quick one from Dan. Digital outputs are designed to be used in DC circuits only or in AC or DC?
So it depends. So most typically those transistor outputs are used in DC circuits, but AC/DC sensors are quite common where the sensor is rated. It's got, for example, a solid state transistor output, and it can be wired for AC or DC operation. So those output circuits can be used in both AC and DC applications.
All right, perfect. All right, so Muslim has another question on LinkedIn. He says, first, thanks for the answers that you've given so far, but what would you suggest for sensing about 20, looks like US centimeters of water particles in a gas tube?
Yeah, and that goes back, that's the same application we talked about. That goes back to a capacitive sensing application. As the water level rises in the gas tube, you can detect it from outside the tube with a capacitive proximity device. So typically they look very similar. I actually have one here behind me. So this is a capacitive device. Typically it's in a plastic tube, so it looks very similar to the similar inductive proximity sensor, but it's plastic material for the tube. Same cable, same output circuit, 3-wire, 2-wire, very similar to apply, wire, connect. And then this is the sensing face that points at the tube as the water rises in that gas tube and passes, a certain distance in front of the face of the sensor, above the level of the sensor, it will be detected and the output will switch. So very similar to an inductive application, but using capacitive technology, which is just a different variant on the sensor transducer and the electronics inside.
Got it. All right, Mario from LinkedIn has a question. What is perfect prox and where would you use it?
So perfect prox, great question, Mario. Segue to our next Ask the Expert session on optical sensing. So perfect prox is a trade name for an photoelectric sensing technology. And I'll give you the example of that, you were talking about success stories earlier, and that inspecting for that bolt that was welded onto that metal plate. So you can inspect for that with a inductive sensor like we talked about. But you can also inspect for that with something like an optical sensor. And when you're using an optical sensor, that typically has much greater range sensing distance. So instead of 10 millimeters, that optical sensor might see 400 millimeters. You want it to see that bolt, but you don't want it to see the metal behind it, because if the bolt's not there, you want to detect that as a fail, as a product rejection. So that type of sensor is known as either a background suppression or a background rejection sensor, and perfect prox is a trade name for that technology. So it sees in the sensing zone optically, but it does not see beyond the sensing zone. So you can do an inspection like that with either an inductive sensor, as we talked about earlier, or with an optical sensor that has that background suppression performance. So a great tool, not an inductive sensor, but a great tool for inspection and quality control in a process or on a piece of equipment.
All right. So next couple of questions. Syed on LinkedIn and Roshan on LinkedIn are asking about some more details on the Iprox series, and then also just what are some things that set our Prox sensors apart from other ones that are available out there? Okay.
Yeah. So it's an interesting question. So there's a sensor called the Iprox. It's an Eaton proprietary technology. But what it is a standard sensor. It looks like this, actually. This happens to be one right here behind me. So it's a standard sensor. You plug it in. It works just like we've talked about for this. But if you want to customize it to a particular application, you can program it. So it's a PC software tool, a USB programmer that attaches to the front of the sensor and allows you to customize it slightly for your particular application. So that inspection application is a good way to describe how this might work. So this sensor out of the box has a range of 10 millimeters. And when you set it up in that application to inspect that bolt, you realize, well, you really need this sensor to have a range of only about 7 or 7.5 millimeters, because 10 millimeters, it detects the plate and it doesn't work as a quality control. But you can't physically move the sensor. That's just where it is in your piece of equipment. So what do? That programmable sensor technology allows you to attach a programmer to the front of the sensor, and then on your PC, in 45 seconds, say, I want it to see 7 millimeters. And so it's not, you don't need it all the time, but in an application like that, it can be very useful to take a standard sensor and be able to adjust the range performance. To the kind of second part of the question about what's different about our sensors, I'd say going back to the point about shock and vibration that was asked a few minutes ago, one of the things we have become very good at over time, because we've been selling sensors and applying them in difficult applications like those stamping equipment applications, presses, those kinds of things. We've learned how to develop high shock and high vibration performance ratings in a sensor. So that's an area where if you have those types of applications, we typically have sensors that can survive in the most difficult places because of that shock and vibration performance.
Got it. Perfect. All right. Well, I think that's all of the questions that we've gotten online. So Eaton Nation, mad props for coming through with these questions. Matt, before we get into the training manual, any last details you want to throw out in the next 30 seconds?
No, I'd just say it's fantastic. I really appreciate all the questions, feedback, input, participation. It's fantastic. I think it's, we did this session because we know inductive proximity sensors look relatively straightforward, but they're not simple to apply in many cases, and wanted to, again, demystify them a little bit, help you understand, the parameters for applying them, in a particular machine environment, and then hopefully open the door to you to understand the power of applying sensors like this, presence sensors, in improving the throughput of a machine or improving the quality of a machine's output. So for a relatively inexpensive device that's relatively straightforward to apply, you can see big gains in the performance of your equipment, at relatively little cost. So we hope that opens a few doors for you in that regard. And hopefully this training manual that you're going to be able to download here in a second can fill in the blanks and things that I didn't answer completely, or the questions that didn't come up. Again, just want to say I appreciate everyone's participation. Thank you.
Cool. Yeah, let's go ahead and get that graphic up. So everybody should be seeing on the screen a QR code. And this is how you're going to download this training manual. So what I need everybody to do is pull out your smartphone or tablet, open the camera app, and go ahead and point it there. So once again, open the smartphone, camera, or tablet camera app. You don't need to open any kind of particular special app. The normal camera works. It's going to go ahead and zero in on that QR code, and you'll see something that's going to pop up and ask if you want to follow the link. Go ahead and click yes. And so one more time, just go ahead and find the camera on your smart device, point at that.
I'm going to try it, Josh.
Yellow bracket's going to pop up. It's going to ask if you want to follow that link. Click yes, and that will take you to...
Works.
Yep, there you go. So that's going to take you right to the training manual where you can learn a ton more information on Prox sensors and how to apply them. And then, of course, make sure to reach out to the Eaton technical people if you have any questions as well. But we're going to go ahead and post that code on the event page at the end of this broadcast, which is coming right up on us. And to learn more about inductive proximity sensors and how to address any application issues you have, please visit eaton.com/E57. And once again, that's eaton.com/E57. E57. Matt, thank you again for joining me for this last session of 2021 for Ask the Expert Live.
Thank you, Josh. Thank you, everyone.
Thank you, Eaton Nation. We'll see you again next year.